Hey, good afternoon, Umang.
Hey Siddharth, am I audible?
You are.
All right, cool. Good. So I guess we'll start in 2 minutes. Is that fine?
Sounds good. So one thing, Umang, can you just keep an eye out on the chat in case there are questions? Just
Sure.
interrupt me and yeah.
So I'll interrupt you and I'll ask. Okay, cool.
Yeah.
That's fine.
Also, I guess, do you want me to make an explicit announcement saying that, people should feel free to ask questions during the talk or?
Yeah, it's better if it comes from you.
Okay.
I think that makes sense. And I'll stop you in about an hour.
Sure.
Whenever we start here. Should I start, Sushmita, do you think, or you want to wait? Yeah, okay.
Yeah.
All right, cool. So welcome everybody to the afternoon session. It's a pleasure to introduce Professor Siddharth Burman. So Siddharth did his PhD at the University of Wisconsin-Madison, and then was a postdoc at Caltech for some years, where we shared an office. Following that, he joined ISC. So Siddharth has received many awards for his work, including Ramanujan Fellowship, the Pratiksha Trust Young Investigator Award, and the International Academy of Engineers Young Engineer Award as well. He works in multiple areas, including approximation and online algorithms, learning, and game theory. And today he's going to talk about fair division, particularly, I think, focusing on welfare maximization. So this is an area that's quite popular and has multiple applications. And I think he's also going to combine it with online algorithms, including, maybe touching on some work that he did with the algorithm as well. So I'm glad that we're getting to hear about it. Siddharth, please go ahead.
Great. Thanks, Umang, for the introduction. Thank you to the organizers for the invitation. It's encouraging to see a flourishing algorithms community in India. So I'll talk about multiple joint works. I'll mention the specific co-authors when I get to the technical results. Also, feel free to sort of interrupt in between and ask question or share feedback. So yeah, you don't have to hold your questions till the end. You can just ask them as the talk progresses. Let me.
Sorry, I'm just going to interrupt one more. I just want to ask participants to please mute themselves if you're not asking a question. There were some interruptions earlier, so it's better so that could continue.
Great.
Yeah, unless you have questions. Great. Sorry, go ahead.
Thanks. So let me start with the following observation that typically, quite often we use the arithmetic mean, the average, and quite often without much thought as a standard way to combine numbers and assess quality. And there are many practical examples, like think of CGPA, the cumulative grade point average. That's nothing but the average of your grades across the semesters. Or like ranking products, looking at their average rating. So that's again an arithmetic mean of ratings using which you sort of rank objects on e-commerce websites. And even in academic circles, we use average number of students graduated, citation counts, and so on. So this as a metric of performance, as a quality measure. And this is not just confined to, say, pedestrian applications, even in settings where the objective functions are revered objects, things like in many AI and ML contexts, we end up using arithmetic mean as the default performance metric as the default objective function. So for example, think of accuracy in your classification settings. That's nothing but the average of the performance of your classifier across different data points, across different data sets. Regret, which is sort of a very the standard performance metric in online and reinforcement learning. Cumulative regret is also the arithmetic mean of the algorithm's performances. So fine, like that's a, if we are looking for allocative efficiency, then arithmetic mean is a important metric. But the point I want to emphasize, the high level takeaway of the talk, is that there are other ways of combining numbers. There are, and especially in contexts where fairness and collective welfare are important considerations, one must sort of revisit this like this default or knee-jerk objective function of the arithmetic mean and try to understand if there are better alternatives. So I will define what generalized means are, and I'll like spell out what do I mean by axiomatic support. But what I want to say is that this is rather a distinguishing feature of the entire exercise that we'll sort of conduct for these two lectures. That is that I am going to give you a class of functions, a family of objective functions, a family of welfare functions that enjoy like fundamental axiomatic support. There are axioms that are very natural in fairness context, and I'll give you a family of functions that actually will characterize these axioms. So this is going to be a rather, my focus will be on algorithms, but this is something that I'd like to impress upon right at the beginning. This is not only based on your aesthetic senses and saying, look, here's another interesting problem, here's a very natural function to look at. This entire endeavor has a axiomatic support and like very classical textbook axiomatic support. And of particular interest in this family of generalized means will be what is called a Nash social welfare. So I'll spell out the technical details in a minute. But this is one member of this family, an important member of this family of generalized means. This is the geometric mean of values. So down the road, 3 months from now, if you want to remember something, just remember that, geometric mean could be an important objective for you to study. It both algorithmically interesting and it enjoys these fairness axioms. So that's sort of the overarching theme of the talk. This is sort of the takeaway. And these means, both geometric and like the generalized family, are relevant in many contexts, in particular like the AI and ML context that I specified. But our focus will be on fair division context, fair division settings, where I would want to distribute certain resources, certain goods among partition goods or resources among n agents to maximize a welfare objective, and a welfare objective that has axiomatic backing. Throughout, whenever I say the word agent, I mean people or entities participating in this division exercise. So I'll have goods, certain resources, I'll be distributing them among entities. These people, these entities are going to be referred to as agents. And I'll just use N to denote the number of such agents. I've designed the talk to be really sort of minimal in terms of notation, but N is sort of something that I'll just carry forward. So let me be a bit more specific. So imagine that I divide the partition or divide or allocate these resources among the n agents, and it induces these n values. So based on what each agent got, V1 through Vn are their values. So V1 is the value which agent 1 accrues under a specific division. V2 is the value of the second agent, and so on. So I have these n values. Different divisions will induce different values. The question at hand, the basic question at hand, is how do I assess the quality, quantitatively assess the quality of this division? What is my welfare objective? So the most natural one, like the one that I started out with, is the arithmetic mean, also called social welfare or utilitarian welfare. It's just the average of these values, right? Fine, a great measure if your key focus is allocative efficiency, but it's not hard to see that this is not not a nice metric to have, or not a nice metric to maximize towards, or not a nice metric to judge divisions by sort of very standard critiques. Things like, if I could give you a division where 1% of these agents own or are given pretty much all of the goods, right? So this 1%, 99% thing, in that case, the social welfare, this arithmetic mean can be high, but it's not a fair way to divide things. In economic thought, this is called Benthamite objective. I'll use the word social welfare. It's like Pavlovian for me. And this is without a moment's thought. I'll just, whenever I say social welfare, I'll mean this expression, the arithmetic mean. But yeah, if you want me to sort of repeat what it is, just stop me and I'll be happy to do that. The other important metric in this space, which is purely a fairness criterion, is what is called egalitarian welfare. So I pick a division, I look at the induced values by the division. So agent 1 is getting V1, agent 2 is getting V2, so on and so forth. So throughout, n is the number of agents, the subscripts will denote the agent's index. So V1 is agent 1's value, so on and so forth. And egalitarian welfare looks at a division and says, okay, I want to maximize the minimum value across all the agents. So it's the min across these VIs, and divisions that achieve high egalitarian welfare are fair. Like they are, and this sort of comes from this Rawlsian criterion of justice, and this welfare is also referred to as the Rawlsian welfare in literature. So these are two extremes, one which is purely looking at a fairness consideration and might sacrifice allocative efficiency. The other end the spectrum is arithmetic mean, which looks purely at essentially at allocative efficiency and looks at the arithmetic mean. So what I'll define is a family that will encompass both. In fact, with a single parameter, it will cover this entire spectrum, and an important middle ground, axiomatically important middle ground, is achieved by this geometric mean, which is referred to as the Nash social welfare. And this is nothing but the geometric mean of the valuations that the agents acquire under any distribution. So these are the three important welfare functions I'll be sort of starting out with. And indeed, Nash social welfare achieves a balance between the two extremes, by which I mean it's a mean. So it's at least the minimum value. So you have this left-hand side inequality. The arithmetic mean, geometric mean inequality tells me that the geometric mean is less than the arithmetic mean. So I have this inequality. So for any division, and hence for any induced collection of n valuations, you will have this inequality. And the idea is, okay, instead of focusing on just one extreme, how about looking at this entire spectrum and trying to design algorithms that perform well for those. And yeah, I will stop harping about the axiomatic thing, but to me, that's quite important. And in particular, these functions that I'll define in a few minutes satisfy what is called the Pigo Dalton principle. It's a fairness axiom, and it says that we want a welfare function, a mean, if you will, a way to combine these values such that informally Robin Hood operations improve the welfare value. That is what Pigo Dalton says, is that if I take epsilon from a high VI, epsilon value, and give that epsilon to a low VJ, the welfare function value should increase. And you can see that, fine, like in Nash social welfare, that is indeed the case. In fact, it strictly increases. If I balance out the VIs by some other distribution, the geometric mean of values increases. So that's one axiom that is satisfied by Nash social welfare and other members of the family that I'm about to define, other members of this generalized mean family. The other important axiom that's satisfied by Nash social welfare is that it is scale free. That is, it doesn't matter in what currencies the agents are looking at their values. So I can be looking at my values, say in rupees, Umang might be looking at it in dollars, so which is that multiplying by some positive integer, positive real number. Even then, the ordering among the allocations or the divisions does not change. Right? That's another important axiom. There are others like symmetry, independence of unconcerned agents. And in fact, there's a set of natural fairness axioms, and the family of generalized means and in up to standard transformation characterizes those axioms. That is, these functions are exactly the ones that will satisfy this axiomatic grounding. Fine, I will stop talking about axioms, but yeah, it's important to appreciate the sort of the bedrock on which all these functions are built. They're not just natural candidates when talking about fair division, they are in fact axiomatically the class of functions, or the class of welfare functions to look at. So I think there's a chat question. Oh, what do you mean by symmetry here? I mean, if I give you a division such that the valuation kind of permutes across. So I look at two divisions wherein the valuation, the collection of valuations is the same, it's just been permuted across the agents, the welfare value stays the same. So yeah, I guess that answers the question. If not, you can just let me know. Okay, fine. Yeah, Umang, can you just keep track of the chart and let me know if there's...
Yeah, sure.
So the family of functions I'm going to look at will have this following form. It is parameterized by a single term p. So there's an exponent parameter p, and as I change p, I get different means, different instantiations. And it has the following form. So it looks at the pth powers of the valuations that the agents have, the n agents have under different distributions. And then I take their mean, take their divide the sum by 1 over n, and exponentiate the whole thing by 1 over p. So it does look like a norm, but there are two things I want to point out. The first is that there is a 1 over n here, unlike the standard norm definition. And the other more important one is that this is actually meaningful for values of p that are less than equal to 1. So p norms are convex, they are norms for when p is more than 1. Here I'm looking at p means, p generalized means, and the range of p that I'm interested in is p's that are less than equal to 1. So when I set p equal to 1, I get the standard arithmetic mean. This just reduces to this expression. When p tends to 0, this expression tends to the geometric mean. This is a exercise in L'Hopital. And here, when you do this calculus exercise, you'll see the relevance of this 1 over n. And when p tends to minus infinity, I get the minimum value. So that's the egalitarian welfare. So as I change p, I get this entire family of welfare functions, which are the family of welfare functions that satisfy a set of fairness axioms alluded to in the previous slide. So p equal to -1 would be the harmonic mean, so on and so forth. So this is our theme. This is the protagonist of the two talks, and I'll throughout focus in various contexts. I'll focus on dividing goods to maximize this welfare function. So that's the overarching theme of the talk. So, okay, that's what the talk is going to be about. What is the talk not going to be about? What are things that I'm kind of punting on? And hopefully someone will talk about this in the next edition of Recent Trends. There are many other notions of fairness. In particular, NB freeness is a very sort of quintessential fairness criterion. I could have very easily centered both the talks on NB freeness and variants thereof. Yeah, I thought there are more open problems in this welfare thread, so I picked that. There are things that look at markets and constructs called competitive equilibrium with equal incomes. It's another important notion in this broad social choice theory, fair division literature, many others. I am going to focus on goods. So throughout, I'll look at cases where the values that the agents acquire under different divisions, under different subsets of goods that are allocated to them are non-negative, but you can also think of chore division. So dividing things that are negatively valued. That's another important line of work. I'm going to focus on settings where I presume that I'll know these agents' preferences, I know these valuations. Of course, game theoretic ideas like what if the agents are strategic, truthful mechanisms, so on and so forth are quite important as well. I'll focus on cardinal preferences throughout. That is, I'm going to assume that agents have numeric values to fractions of goods they get or bundles they receive. There's also a line of work that looks at ordinal preferences, like where you don't have numeric values associated with divisions or subsets or fractions of goods. Rather, you just have an ordering that I prefer this over that, and so on. I'll also not talk about monetary transfers. That is, I'll only assume that there's a division and no subsidies, or I can't pay money to sort of like cover up fairness gaps. Even in the context of formulations, there are many others. So like, yeah, the one line summary of this slide is there are many other things. At the end of the talk, I'll give you textbook references where you can look this up and some recent surveys. But yeah, like in terms of alternative formulations, for things like wealth gap or income inequality, organizations like the World Bank use metrics like the Gini coefficient, Renier entropy, Jaynes index, and there's in fact a alternative axiomatization in network resource allocation context called the Lang-Chiang axiomatization. So yeah, this is all that is I'm not going to cover. This is what I'm going to focus on, P-mean welfare. And so like, yeah, for the two talks, this is going to obsess about maximizing this function for values of P that are less than equal to 1. Let me just pause for a second and see if there are questions or.
Nothing so possible.
Okay.
Besides the one you answered.
Excellent. So before I get to the technical things, let me point out some applications. I have two, there are two purposes here. The first one is that I want to impress upon you the fact that this is not all stylized exercise. There are real world use cases for what I'm talking about. So these are applications with empirical backings. The other motivation is that through these applications, I'll be able to extract out a taxonomy, which will let me sort of organize the like literature. It will let me organize the remaining parts of the talk. Okay, so the first fair division application use case I want to talk about is this work by Deng et al. This was done in Singapore in the context of public housing units. So Singapore allocates housing units across families. So these are government-owned houses that are given out to families. The point here is that the resources being allocated are houses, they are like apartments. The agents participating in this fair division exercise are different groups of people. So one, like in particular, Singapore by law would want to ensure fairness across different ethnic groups. So that's a nice sort of context where what I'm going to talk about is applicable at least at an abstract level. And in particular, Benabao extracted out a very nice mathematical framework for this setting. And so that's also worth looking at. The point I want to focus here is the resource or the good being allocated is an indivisible entity. It's a house. So it doesn't really make sense for me here to say that, oh, 2/3 of the house is given to this family, 1/3 to some other family. That really doesn't make sense. So here it's a discrete, it's a combinatorial problem where I want to allocate housing as an indivisible item, as an indivisible good to each agent, to each family. That's application one. The second, which has been rather influential, is this work by Budish et al. So this is a tool that's used in Wharton to fairly assign a course allocation among students at Wharton. There's a previous paper by Budish by himself, which has been quite influential in sort of defining some fairness notions that are useful in the indivisible goods case. And here too, the resource being allocated are course seats. So every course, say, has an upper bound, has a limit on the number of students that can credit it. Different students are the participating agents in this exercise. They have different preferences, different specializations, different choices among courses. You want to divide them, allocate these seats among the students in a fair manner. So here again, the good that's being divided is indivisible. Different agents have different preferences. You would want to sort of find a fair division. So again, a use case where what we'll talk about, at least an abstract level, this will be useful. Third example that I like is by a study by Alexandrov et al. This was done in conjunction with Food Bank Australia, where they have a hub. Food donations come in and then they distribute this. So every day they distribute this accumulated food across soup kitchens across, say, canteens. So I know, for example, ISKCON does a similar thing in Bangalore. I'm sure there are other organizations in India that do that too. Yeah, the takeaway, the sort of thing I want to highlight is that here the resource is food, which is essentially divisible. If I have 10 kgs of rice, it makes sense for me to say, okay, 2/3 of this goes to the first soup kitchen. There are more people waiting in queue there. 1/3 of this 10 kg of bag of rice goes to some other soup kitchen and so on. So unlike the first two cases, here the goods are divisible. And though the challenge here, and this is something that I'll sort of actually delve in detail, is an online aspect to it. I get a batch of food, some donation for that day. I have to distribute it. I cannot wait till I get till the end of the month to make a allocative decision. So there's an online aspect to it, which I'll address in tomorrow's talk. The third example is the study by Suzy. This was done in Nigeria. They're dividing electricity, so load shedding, as it's called in Nigeria. They want to understand what is a fair way to do that. So here again, the resource is electricity. You have some megawatts of that's being generated. You want to distribute it among different parts of the city. Say, how do you do it so that overall, say, in over a month time or over some time window, you are fair? The point to note that here there's a contiguity requirement. You cannot sort of give electricity for 5 minutes, cut it, give for 5 minutes and cut it. So while electricity has this fractional feature to it, there is a way to say, okay, I'm giving you 10.3 kilowatts of electricity. There's a contiguity requirement in the temporal sense. So yeah, different contexts, in all of which the welfare functions I talked about make sense, but the underlying context is different. Some have a divisible flavor to it, some are continuous optimization problems, and some are discrete optimization problems. So fine, I'll also quickly mention this widely used platform called Splitit. It's quite often used for fair division of many things, such as rent among flatmates, credit division in a project, or dividing inheritance among siblings. So these are the applications. I'll jump into the math and the algorithmic framework, but let me just mention one thing, that our focus is going to be instrumentative. I'm talking about algorithmic contributions. I'm not raising a debate about normative things, in the sense that I'm not saying, okay, there's a debate to be had, especially like the use of algorithmic and machine learning tools in socially sensitive decisions. That's not my agenda. My aim is to develop tools that practitioners can use. So that, yeah, I'm approaching this as a computer scientist. Fine.
There was a question from Sushmita, I believe.
Yeah, hey, please.
Hi. So that application of Budish et al. On courses,
right?
Fair division. So the scope of that modeling, is it different, very different from that, what we are able to do using matching, like stable matching, rank maximal, all those sorts of things?
There's a, so yeah, like this is like, what you're saying is like a more like an ordinal preference. I hear there is a numeric kind of a thing. The other thing is like, it's not unit capacity per se, it's like in a matching. So you might be able to take 3 courses or 4 courses and so on. So it's more like a B matching setup.
Right.
But yeah, I guess like one way for me to sort of allude to that question is it might be, it's like a hospital
right.
version of it.
Hospital, exactly, the lower capacity, upper capacity, when you have those sorts of things, right?
Right.
And there are the sort of a canonical way of transferring, at least in the context of matching, ordinal to cardinal, cardinal to ordinal. Like you can interpret the rank preferences as a cardinal utility function.
Yeah, so instead of stability, like, or blocking as my criterion, I want fairness. So there might be blocking things, but I really here, what I care about is like a welfare across the entire batch of students rather than stability. Also, I don't have preferences on the other side, as in if there are 100 seats, like typically the instructors should not be like getting to cherry pick which students can take that. So that's also another, like, I think differentiating feature between the two.
Okay, so it's I see. So one thing is that there's no notion of blocking pair, but you are trying to optimize an objective function, and these means characterize those things, and possibly there's no preferences from the instructor side. It's the utilities are from the student side. That
Exactly. Yeah.
Okay. Thank you.
And there are no transfers here, as in like it's sort of in bad form for me to say, okay, you didn't get this course. Here you go, 100 rupees. Enjoy. Yeah, here's a pizza on me. So that's not sort of kosher in this context. Yeah, but it's a good point. I mean maybe it's like my bias, but like when I see matching, it's in fact the question I ask is why not Nash social welfare there? So that's my sort of response to looking at things like recommendation system and all. Instead of stability, why not Nash welfare? So like but I guess that's a perspective or a problem formulation thing, which is somewhat context dependent. So yeah.
Thank you.
There is also a question on chat. Do you want to read it out?
Let me just read it easier maybe.
Yeah.
Are there some theoretical applications of P means? Yeah, exactly. So when you say theoretical applications, that's slightly oxymoronic to me, but fine. Yeah, I see where you're getting at. Indeed, yeah. So Pareto optimality is one criterion that I did not mention because I don't want to define Pareto optimality, but yeah, it does have connections. I mean, the undercurrent of what I'll talk about are those connections. I will, in fact, show you the connection in the other direction. I'll start with approximate NV freeness and end up at approximate Nash social welfare maximization. So yeah, it has connections and very interesting ones in very varied contexts. So yeah, that's sort of the short answer of it. Okay, so I talked about, is this good? Can I go on? Slightly behind schedule, but yeah.
Yeah, I think please go ahead. That's fine.
So we saw these applications. Inspired by that, I'll give you a taxonomy. It's a rather simple one, and based on that, I'll sort of structure the remaining parts of the talk. So it's quite as simple as like looking at whether you are facing a continuous optimization problem or a discrete one. So you can look at the resource that's being divided. It can be divisible, it can be indivisible. So divisible things like food, land, water, indivisible like housing units and courses. And so that's one way to partition the results. Furthermore, divisible goods can be heterogeneous or homogeneous. So heterogeneous, think of it like land. So a stretch of land, say in South Bombay, is much more valuable than the same length of, say, in Bangalore or in some outskirts of the city. So there are these heterogeneous resources like spectrum allocation or transmission rights. So 10-minute advertisements, like a 15-second advertisement slot after an IPL match is much more valuable than a 15-second after, let's say 4 a.m. in the morning. Or the divisible good can be homogeneous. It's like 10 kgs of grain, right? So if you get half of it, your value is half of the total value. It's a homogeneous good. So these heterogeneous goods are typically referred to as cakes, and the ad nauseum analogy being that different parts of the cake have different icing, so the value changes. These homogeneous types of divisible goods are typically studied in market settings. So I will not focus on markets, but I'll get to it. And the indivisible ones are typically referred to as discrete fair division. That's a combinatorial problem. I will cover all the three leaves, or at least I'll try to cover all the three leaves. So today, what I'll do is start with cake division. So the leftmost heterogeneous divisible good. I'll talk about Nash social welfares for this. So I'll try to maximize geometric mean in this setting. Tomorrow would focus on the remaining two leaves. I'll talk about generalized mean welfare for these two contexts. So that's the sort of organization of the talk. And since I'm running late, let me just jump right in and let's start with some dessert. Cake division. Okay. So cake is used to refer to a divisible heterogeneous resource. Divisible in the sense that here it makes sense to allocate fractional parts of it. So a subinterval can be assigned. Heterogeneous in the sense that different parts of the resource are valued differently by the agents. And this is a very well-studied area of work, like almost 7 decades of research behind it. the seminal work of Stenhouse that sort of laid the mathematical foundations of fair division was conducted in the cake division context. There are textbooks written on it, many popular science videos on the internet. It plays a very important role in this bigger umbrella of fair division literature and social choice literature. And almost all the central solution, fairness solution concepts are sort of developed in the cake world, and then they sort of morph or sort of mutate into other contexts. So there's a very small chosen list of references. It's a huge literature. There are more textbooks just on cake division and its uses in like border disputes, so on and so forth. So like the basic protocols in this space, like how to divide a cake fairly among two agents. In fact, that method has literally a biblical reference. So yeah, this is something that has been studied for quite some time. A bit more formally, the cake is modeled as the unit interval 0, 1. So the agents prefer subintervals. So that's the divisibility aspect of it. The heterogeneity is captured by the cardinal preferences, these preferences of the agent. So what I have here is the unit interval. I want to divide this unit interval, that is, give each agent a piece of this cake, 0, 1, a connected interval. And how are the preferences specified? Well, they're specified by a function VA that tells me what is the value of this interval I for agent A. So again, throughout, subscript means the agent's identity. And here, if it helps you like visualize things, imagine that there's a probability measure over the unit interval, and agent A's value is nothing but the probability mass with respect to this density function. It's this area of the curve. So for this interval and this density function of some agent A, VAI is A's valuation for this interval I. If I look at some other interval J, the area under the curve, that would be the valuation for this interval capital J for this agent A. So always remember, subscript is agent's identity. So what do I want? I want to partition this resource, this interval 0, 1, such that each agent gets a connected piece, gets an interval, a subinterval. So these intervals are assigned again based on agent's identity. So I1 is the interval that gets assigned to agent 1, I2 is the interval that gets assigned to agent 2, so on and so forth. So in this figure, the leftmost interval goes to agent A, then the second interval from the left goes to agent B, and so on. Every agent has her own valuation function, and they evaluate the interval they receive based on their preference, their valuation function. Note that the results I'll talk about do not require me to have explicit knowledge for these valuation functions. A standard Oracle model will work. So that's just a side note here. So my output, what I want to find in some sense is n-1 cuts. So I'll make n intervals and assign them among the agents such that some fairness criterion is satisfied. So in this line, the fundamental notion of fairness is what quintessential notion of fairness is what is called NV freeness. And here it is. What it says is that, oh, I want a division such that every agent is satisfied with the interval that she receives. So I pick any pair of agents A, B. A looks at the value she receives for the interval that's been assigned to her. So VA is A's valuation, IA is the interval she has received. So that value should be at least as much as A's valuation for any other agent's interval. So note that both sides of the inequality are evaluated with respect to VA. So A is satisfied with the interval IA that she has received and would not like to swap with anyone else. So that's the central construct here. Haven't seen this. The next thing I'm about to say should surprise you. It still surprises me. And point is that, okay, isn't this too strong a requirement? I haven't imposed anything on the valuation. This could be, like n can be very large. These valuations can be rather complex. Isn't this such a tall order? Well, as it turns out that under very mild conditions on these valuation functions, one can show, in fact, Sue showed, that an NV-free division always exists. This is a super surprising result. The proof uses Sperner's lemma. combinatorial analog of Brouwer's fixed point theorem. It's a delightful proof, right? Almost as delightful as eating a nice piece of cake, right? And as internet as my witness, I love talking about it, so much so that I thought, okay, let me not do this again. If you want, I can just give you video references, but this is a proof from the book, like one of favorite things in this line of work, something that I strongly recommend that you go and watch or read. Even the original paper is very well written. So that's a major result. It's a major existential result that says that for very mild conditions, in fact, like all you need, say, for example, is that these VAs are continuous. So as long as that happens, an NV-free division will always exist. So this is a rather non-obvious fact, which, if you haven't seen it, should impress you. This is the only exclamated result I'll have in my entire slide deck. But as it so happens, you have a question?
Yeah, so this value, this allocation thing, it can leave some portion of the interval unassigned?
No.
Okay, so an empty
complete
allocation is not possible because that would always be NV free.
Exactly, yeah. The entire cake is partitioned into, like, it's not disconnected. Every agent is getting one single connected interval.
Okay.
Yes.
Okay. Okay.
So I have a question.
Yes, please.
So how is this different from the perfect partitioning of the cake? Like,
so perfect means that your value for all the intervals is the same. So it could be that VAIESA is like 0.9 and VAIB is 0. So that would be NV free. I get a piece that I value a lot and I really don't care. Like I like cherry and you actually gave me the part of the cake that has cherry, and I really don't like vanilla and the rest of the cake is vanilla and you gave it to others. So that is not a perfect division. Perfect cake division, the definition is slightly different. Yeah.
No, I'm talking about this result by Noga, Allen, or something. It's this.
Yeah, I know.
Can indent the cut, right?
Necklace splitting. Yeah. So those are, the number of cuts are different too. So they for a perfect division, and in this case, you'd need something like more than n cuts. So in fact, 2 n.
Okay.
Yeah. Does that make sense?
Okay. So here, apart from this, nothing is known that if we impose the this restriction on number of pieces, then this is like we need these mild assumptions. Like nothing like those perfect partitioning exist here.
So those perfect partitioning also don't require too strong an assumptions, but the requirement of a perfect cake division is stronger. It says that VAIB for all A and B is the same.
Okay.
So I can, like, in that effectively means that, and that does not work with n cuts. You can come up with simple examples. So there, like each piece would maybe have, let's say on average 2 pieces, like each I would consist of 2 pieces. So here I'm saying a single interval per agent, there it might be 2. But then the point is that you have this cut and you can just arbitrarily assign it among the agents and it will be perfect. So it's a more demanding requirement. However, the number of cuts then goes up. So each agent in that case can get 2 pieces or on average 2 pieces. So does that make sense?
Yeah, thanks.
Maybe if you want, we can talk about it offline too. Like even the under the hood, the results are different in the sense that this uses this is a PPAD argument, like a fixed point theorem or Sperner. Those are more Bourchier-Coulomb type arguments. So they go up a complexity class, they fall in PPA. So there's necklace splitting, and there's some recent very nice work that shows that the similar problem called consensus halving, and even those are like the complexity, even at a complex, like computational complexity level, the problems are have different underlying flavors. So yeah, I'll not talk about perfect cuts, but yeah, maybe offline we can chat a bit more about it. Yeah. Excellent. So yeah, major result by Su. What I want to say is that this is purely an existential paradise, right? Like nothing about this result gives me an algorithm. In fact, even if I relinquish this requirement that every agent is getting a single connected piece and I allow for crumbs across the agents, the best known algorithm that gets exact NV freeness runs in hyper exponential time. So it towers of 6n. That's the best known algorithm, even with disconnected pieces. And if you think this is bad, let me actually rub salt in this wound and give you this very strong negative result by Stromquist that says that, let alone a exponential time algorithm, there's no finite time algorithm for this if the valuations are being specified by an adversary. That's a strong negative result. In fact, holds for 3 agents. Okay, so why am I doing all this? Like, I have enticing you with a cake result and then telling you nothing is known algorithmically. And in fact, I've like digressed into this world of NV freeness and have somehow not talked about welfare and Nash welfare or generalized welfare for the past few slides. Well, the reason is because positive results can be obtained if we look at approximations. So in this joint work with Ishwar, Rachitesh, and Nidhi, we showed that if you have approximate NV freeness, you in fact also get an approximation guarantee for Nash social welfare. I'll formally spell out what both sides mean, and I'll give you the exact reference at the end of the talk. But yeah, the 2 interesting points here is that there is connection between the NV freeness and Nash social welfare, even when we have approximate NV freeness. And towards the end of the talk, I'll show you a polynomial method that finds approximately NV free allocations. It bypasses the Stromquist result by finding not exact NV free, but approximately NV free allocations. The next slide, I'll define precisely what I mean by approximate NV freeness. Okay, so that's the agenda for hopefully the next 20 minutes or so. So here's the setup. Let me just quickly remind you, I have a cake. That's the resource, the interval 0, 1 that I want to divide. Every agent wants a interval. So I subscript 1 is the interval that I assign to agent 1. I subscript 2 is the interval I assign to agent 2, so on and so forth. The agent's cardinal preferences are specified by this valuation function, and I'll only need Oracle access to these valuations. Okay, so here's the definition, rather a natural one. I'll say that a collection of intervals, a cake division, is alpha NV free if the NV is multiplicatively bounded by 1 over alpha. So what this says is that, again, both sides evaluated with respect to A's valuation for all pairs of agents, agent A's value for the interval that's been assigned to her is at least as much as 1 over alpha times the value she has for any other agent's interval. So if alpha equals 1, I get exact NV freeness. See, alpha is 2, that means that my NV is multiplicatively bounded by 1/2, and this has to hold for all pairs of agent. So that's NV. What is Nash social welfare in this context? Complementarily. So I can define, it's the geometric mean of valuations. And in this setup, it will be the geometric mean of these VIIIs. I look at all the agents, look at the value that they're acquiring from the interval assigned to them, that the geometric mean is the Nash social welfare. So right now, these are 2 orthogonal fairness constructs. What I want to do is connect them, and this is the formal connection. What I'll show to you is that any alpha NV free cake division is in fact 2 alpha approximate with respect to Nash social welfare. So there's nothing algorithmic about this. This is just a property of alpha NV free divisions. But what I'm saying is, give me a NV free division where the NV is multiplicatively bounded by 1 over alpha. That allocation will achieve a Nash social welfare that is within a factor of 1 over 2 alpha of the optimal Nash social welfare, of the Nash social welfare that can be achieved by any partition of the cake into n intervals, and then the assignment among the agents. So that's the result I want to prove. In fact, the proof is going to fit in this slide.
Maybe I'm jumping the gun. I just want to ask, so you mean that the alpha NV free division is itself a 2 alpha approximation, right? Will you modify it somehow?
Say that again, Aman. Like
the alpha NV free division,
yes,
is itself a 2 alpha approximation, or will you modify that allocation to get a?
No, it's itself. Okay. Yeah, so if I1, I through In is alpha NV free, that is, it satisfies this yellow inequality, it will have a 2 approximation for the optimal Nash social welfare.
Thanks.
Yeah, I won't even touch it. Yeah. So yeah, this sort of alludes to what was being asked, like what is the connection between NV freeness and Nash? This is one. Actually, there are many, and in like very drastically different. Even in like things where we are dealing with discrete objects, there are very sort of beautiful connections between these 2 solution concepts. And ask me offline why I think this is the right connection. Okay, so this is the joint work. The proof will fit in this slide. In fact, by design, I've picked results that fit in one slide. For flexing technical muscles, I'll just point you to papers. It makes life easier for both of us. So yeah, if you think this is too simple, this is, you can thank me. It's by design. Here's the proof. It actually follows from just staring at this picture. So start off with an arbitrary alpha and V free allocation. So say I1 through In is a n partition of this cake 0, 1. Different agents based on the subscript are getting different intervals. And this is alpha and V free. That is the NV is multiplicatively bounded by 1 over alpha. And at the same time, let me consider a Nash optimal allocation, an allocation that's maximizing Nash social welfare. So among all n partitions of the cake, among all partitions among intervals of the cake, this I star is the one that maximizes the geometric mean, maximizes the Nash social welfare. So in this optimal, and let's fix an agent A, any agent A. In this optimal, agent A is receiving this orange interval, let's say I star A. So I'm looking now, I'm defining the set Ka, which are all intervals in this alpha NV free allocation that intersect with I star A. So let me spell this out. So capital Ka for any fixed agent A are all intervals in the alpha NV free solution that are intersecting with the optimal interval. So note that at this time, I don't have either the alpha NV free solution nor the Nash optimal one. This is completely an analytic exercise, but I can define this, right? Both are like both cake divisions partition 0, 1 into n parts. So fine, I have this collection of intervals, and this is capital Ka. Small ka is defined as the cardinality of this set. So in this figure, for this agent A, there are 3 intervals that intersect with I star A. So small ka is 3, like 1, 2, 3. Okay, so here's the first inequality, which is pretty much on the nose, follows from the definition of alpha and freeness. So what I'm saying is that, okay, if I look at the valuation that any agent A receives in this alpha NV free allocation I, and multiply that by Ka times alpha, then that is at least as much as what A is receiving in the optimal allocation, right? Why is that? Well, this is simply because alpha VAIA is more than each of these, the value of each of these intervals, right? So if every interval in capital Ka for alpha VAIA is more than VA, let's say it's more than VAIB, alpha VAIA is also more than VAIC, and so on and so forth. This is the definition of what it means to be an alpha NV free allocation. There are Ka such intervals. So their union covers I star A. So if I sort of multiply that by Ka, I get this inequality. So with this additional Ka alpha, I value in this alpha NV free is at least as much as the optimal value for any agent A. Okay, fine, just a property of alpha NV freeness and the definition of Ka. And to note that the valuations are additive. So this entire union, the value would be at most this left-hand side. Okay, here's the slick counting thing. And this is probably the only sort of cuteness in this proof. And the point is that if I look at the average value, the arithmetic mean of these Ks, then that in fact is no more than 2. Right, so there are n intervals in this alpha NV free, n intervals in this optimal. And if I look at this intersection count, a counting argument, you can convince yourself that on average, this Ka value is at most 2, or the sum of these Kas is upper bounded by 2n. Right, so they're only like the right end points of every IB is for one interval. It's only the last interval that sort of contributes to 2 I star A. So if I'll pause here, like take a sip of water, but hope that you're convinced with both these inequalities, because that's all I'm going to use to establish this lemma.
And like you're not assuming over here that that IA star is contiguous, right? It can be this.
I am assuming that.
You are, okay, I see.
Yeah. So yeah, if like it's like, I mean, the sum is 2n, which is the sum of intervals here and the sum of intervals here.
Okay.
So if it had many pieces, then this would go up. It won't be 2n. Like if you bring this n here, it won't be 2n. It will be the number of intervals in both.
Okay.
Yeah. So I am using that, but it's a fair comparison because I'm looking at Nash optimal only across cake divisions where every agent is getting a contiguous piece, like a connected subinterval.
Yeah. Okay.
Okay, so actually I'm done. This is all I'll need to prove this lemma. Why is that? Here it is. So let's start with a Nash optimal solution. So this is the best possible Nash social welfare you can achieve across all cake divisions where every agent is getting a single interval. So that's the geometric mean. Great. I can pointwise replace this value by the left-hand side. So just plugging in this inequality. So if I have this additional multiplicative factor of alpha Ka, then I have this inequality. It's a pointwise substitution. The geometric mean is monotone. Fine. So alpha is a common term, pops out. This is a product. So I can write it as a geometric mean of these Kas and separately geometric mean of these VAIAs, the values that the agent is getting in this alpha NV free allocation. And this geometric mean of values is nothing but the Nash social welfare of the in alpha NV free allocation. So that's I just write it as NSW. What I'm left with is this geometric mean. Well, I just use the arithmetic mean geometric mean property. Since the arithmetic mean is at most 2, the geometric mean cannot be more than 2. That's it. That gives me the last inequality. So what I get is that the Nash social welfare of this alpha NV free allocation is at least 1/2 alpha of this globally optimal allocation. There you go. We started out with an NV free division, and I've proved to you that it will always be a 2 alpha approximation to the Nash social. That's it. QED.
One question. So here you don't need any assumption like Sue's result. It is even for, does it work for even non-continuous kind of valuations?
I did sum this up, Arindam. Like, so this part, right, uses the fact that the VA of this union is the sum of the VAs of this. But if you have a sub-additive valuation, this will hold true.
Okay.
I have not used continuity here, you're right. I will use it to establish the existence of this. But let me kind of point out a crucial difference. This entire thing I'll pull off even the existence of approximate NV free allocation via purely a potential method. Whereas Sue's result is actually under the hood, it's a parity argument. Sperner is a parity argument on steroids. It's a PPAD. It belongs to this class PPAD, whereas this entire proof I'll give you is a purely potential argument. So that in some sense, I am going to prove to you the existence and like an independent standalone proof to you of the existence of approximate NV free solutions. I will not rely on Sue in that sense. But yeah, makes sense. Is there? Okay, 10 minutes and I'll try to wrap up. 5 minutes, I'll try to wrap up. So that's the connection, fine. What I want to show next, and maybe I'll go overboard by a few minutes, but just bear with me, is that in fact, you can find 2 NV free allocations. And when I say this alpha equal to, I mean that the NV is multiplicatively bounded by 1/2. And I'll give you a polytime algorithm for this next few slides. What these two together tell me is that Nash social welfare maximization and admits a 4 approximation. So in particular, I'll use this result to find a 2 NV free allocation. That 2 NV free is guaranteed to be a 4 approximation, courtesy the lemma that I just discussed. So one point is that this is an honorable desiderata in and of itself. It's a beautiful problem. You can, even if you don't like Nash, I think this is a great direction of study. Finding approximation results for NV free cake division is a noble pursuit in and of itself. So this just happens to be an advantageous sort of add-on. The fact that you get a constant factor, like a factor 2 blow up in Nash social welfare is a great add-on, I think. Okay, quickly, since I'm short on time, here's the final part, which is, so I showed you approximate NV free implies approximate Nash social welfare. Let me give you an algorithm for maximizing, for approximating NV freeness. So it's a very, again, like my promise of single slide results. It's a cute algorithm, a slick algorithm as you see it. So what I'll do is this iterate, like interval growing idea. I'll assign interval to agent starting with the empty one. So PA is the interval that agent A gets, and these PA keep changing, but they keep growing in value. But throughout, as the algorithm marches on, I will maintain I'll maintain NV freeness up to this, let's say, polynomially small term epsilon. So I'll keep assigning larger and larger valued pieces. I'll grow these intervals PA, kind of keep shifting them. So again, PA is the interval for agent A, PB would be the agent for interval agent B, but I'll maintain this as an invariant throughout my algorithm. So what's the idea? So let's say I have these PAs assigned to the agents, and this is not going to cover the entire cake. A large chunk of the cake, say, is unassigned. So U1, U2 are the unassigned pieces. PA, PB are the intervals given to different agents. Now it could be, so what I have is that between agents, they don't envy each other by epsilon, but they can value some unassigned pieces quite a lot. In particular, when you start off, everyone has the empty piece. So the unassigned piece is actually the entire cake. So you are really envious of this unassigned pieces. But what I'll do is, as long as there is an unassigned piece that's envied by any agent, let's say envied by more than this additive factor, small additive factor of epsilon, what I'll do is I'll execute a moving knife over this unassigned interval. So what do I mean? So let's say I have this unassigned interval U1, both A and B value U1 epsilon more than their current interval. So VA, PA is epsilon less than VA U1, VB, PB is epsilon less than VB U1. So they actually would prefer U1 over their epsilon prefer over their current interval. What I'll do is I'll start at the left end of this unassigned interval. So U1 is not given to any agent. And I keep moving the knife, a hypothetical knife, to the left. So here the left end point of U1 just happens to be 0. It could be anywhere. But I'll stop as soon as any one of the agents tells me that now to the left of this knife cut, the interval is epsilon more than my current value. So here, let's say I stop when agent A just so happens to shout that, look, this red thing, I value it epsilon more than my current interval PA. So note that this is the first agent that shouted, the first agent that said that this shaded thing, red shaded, is more than my current value. So no one will actually envy this by more than epsilon because they didn't shout. So what I can do is agent A can relinquish her interval. So the unassigned interval here grows and can take this part, PA. So I have maintained this invariant explicitly by running this moving knife. Over time, but just give me 2 more minutes. So what ends up happening is that at every iteration, the value of the agent increases by epsilon. The total value of the cake is normalized to 1. So this will iterate only a linear number of times. So every agent can sort of change her partition at most 1 over epsilon times. And so after n over epsilon iterations, you will stop. And at termination, what you'll have is that not only do I have NV freeness among the assigned bundles, but I'll have NV freeness among even for the intervals that are unassigned. So let's say I terminate with this. So note that there are n assigned intervals. Every agent is getting, like agent 1 is getting P1, agent 2 is getting P2, and so on. So there are n assigned intervals. So there are at most n plus 1 unassigned intervals. So these U1, U2 can be at most n plus 1. With a smart bit of post-processing, you can actually ensure that there are only n assigned intervals. So these U1, U2 is at most n of these. And then what you can do is simply club the unassigned with an adjacent assigned one. So you look at agent A, this is at termination. There might be an unassigned piece to its right. So you club it. And this is the final interval that agent A gets. Agent B at termination was getting PB. You look at an interval to its right, this might be empty, but in this example, there is one. So you club it together. This connected piece goes to agent B because she was getting PB, so on. So you have n assigned one, n assigned ones, they are interlaced. You just do these pairings, and this is the final allocation. My simple claim to you is that this is half NB free. Why? This is the final equation. Well, if I look at 2 times the value that agent A is acquiring right at the end, this is at least 2 times PA, right? IA is bigger than PA, monotonicity. And so VAPA by itself is at least VAPB. This was the invariant. Also, because you terminated whatever interval was given to PB, in this case, this is U2, you have VAPA is at least PAU prime. So this twice of this is more than the sum of these individually, and with a -2 epsilon because that's the slack. But this PA and U together form IB. So I have, like, again, here I'm using additivity, subadditive would suffice. So what I have is that this sum is more than the value that A has for B's interval. There's a factor 2, and hence this is up to this small 2 epsilon, you have a 2 NV free allocation. That's it. So yeah, you have a question, Shushmita?
Yeah, so the thing is, when we assign PA to agent A and B to agent B and so on, the knife moving thing ensured that A is not envious of B's allocation. But when we assign the unassigned portion U2 to B along with PB, how are we guaranteeing that agent A is now not envious of the new extended assignment to B?
Because the valuations are additive.
Sure.
So the value for this whole thing, which value for IB is value for this plus value for this.
Correct.
And individual, so look at from A's perspective, right? She has guaranteed to receive PA, in fact, something more.
Yeah.
Now, for A, again, everything with A's perspective, this PA is at least PB, and PA is also at least U. That's why I terminated. Otherwise, the algorithm would have marched on.
Right. Okay. Correct. Sorry.
Yeah, this two,
that's the part.
two
Yeah.
things, like the first one is this, the second two is more. That's it. Yeah.
Thank you.
Yeah. So slightly over time, apologies for that. But this is sort of the main theorem. I have a 2 approximation algorithm, 2 NV freeness algorithm, and gives me a 4 approximation. So as I said, this is a great problem. I really like it. If you think back or you read the paper, you'll see that this actually gives us a 1/3 additive guarantee. So this 2 is a multiplicative one. You can, the same analysis actually tells you the bit of thought that the same allocation is actually 1/3 additively NV freeness, that there's the additive NV between any 2 agents is at most 1/3. Now, recent work with Pooja, we sort of improve it to 1/4, and it does require like some like hitting set ideas, and it's like, yeah, it's like, I mean, it's more intricate than the slick idea that I just presented. But yeah, the additive bound can be improved. Improving on the multiplicative one is a great open question. There are positive results for special valuation classes, like there's a work by Nidhi that talks about so-called MLRP valuations, but in general, yeah, getting even a QP task is a great question. Yeah, for welfare, I have some results. It reduces to what is called job interval selection problem. This is a bit classic problem in interval scheduling. I gave you a constant factor approximation for Nash. It's in fact, Nash and other welfare in this range are APX hard. And as I said, it's a great problem to improve upon these approximation bounds, obtain complementary hardness approximation results. And in terms of welfare, this egalitarian world is wide open. There's a 2 in approximability, but there is no non-trivial approximation for this egalitarian cake division. So yeah, that's again a nice question to my mind. Here's the paper that I talked about. This is the Mullen's book, talks about the axiomatic stuff. If the slides are there, these YouTube links will give you the Sue's proof and such. And for some contemporary perspective of fairness in algorithmic decision-making, I'd recommend you read these 2 recent surveys. So I'll just stop here and thank you for your time.
Okay, thanks a lot, Siddharth. That was a great talk. Maybe one quick question before the...
Please.
Does somebody have a question to ask? No? Otherwise, we can do this offline, and you have another session coming up, so we can do
Right.
that.
Yeah. I think I'm.
So I guess we'll take a 5-minute break before the next session. Is that fine, Sushmita? Okay.
Thank you.
So we'll see everybody in 5 minutes.
Thanks.
Hello. Sorry.
Hey. Hi.
Hi. So in that moving knife setting, we are still caring for the cakes to be contiguous pieces, right?
PR.
So what happens when the cake, like the knife moves? So we have allocated one, like 2 pieces for 2 agents already, A and B.
No. Yeah. For 2 different agents. So every agent is getting just a piece, and So can I share the slides again? Let's see if I can. Oh, I think I can do that. Yeah, we'll stop before Kavita comes. Yeah, so you're saying Vishwa. Yeah. So here, it's so right now A is getting this single interval PA and B is getting this single interval PB. Just so happens that both of them value U1 epsilon more than their current piece with respect to their own valuation.
Okay.
So U1 is a large, say, unassigned piece. It
Okay,
can happen.
so the knife is never going to move over one of these assigned cake before somebody already shouts stop.
Exactly. Like if it's too small already, I'll not care.
Okay.
Because at the end, I just want this inequality, which for those intervals, it's not. So it's only, so it's only when this happens that I run the moving knife.
Okay. Yeah. This looks very similar to that Dubin-Spanier algorithm of moving knife.
Connectivity. Moving knife is, of course, very popular, but this sort of a iteration growing, to my knowledge, is not like any non-trivial approximation was not known before this. So yeah, there are like the connectivity and this just moving stuff around is sort of important. Yeah. And again, like this is purely a potential argument. No, like I have not used any parity arguments. I think the slides would be shared by the organizers. So yeah.
Yes, we'll share the slides as well as YouTube links. I mean, absolutely.
Yeah.
Thank you. That was a fantastic talk.
Thank you. Yeah. I went over, but hope I'll try to be on time the next.
No, it's fine, really, because we kept the sessions short, right? Just 2 talks, and there's enough, sort of back end gap. So Kavita can also go over time. Like
Okay.
You take a little more time. That's why it's just.
No. In fact, I was going to say that everybody must be hungry now after so much talk about cake.
Yeah, I know. Like an actual one, like I could have offered this. Yeah. Even if you don't understand this, like here's some cake and. Yeah.
I know we should have had an in-person conference where you gave cake to all of us.
Yes, I found a nice bakery close to my house. So yeah, it's.
So shall I share screen, Sushmita?
I'll just see if they made you a co-host. Yes, please do share. I'm just checking if Meghna is on. Yes, Meghna is also here. So good. Great. I'll just mute myself now.
So Sushmita, hi. The recording will be taken care by the organizers, right?
Oh yes, absolutely. Even I'm not doing that. So broadcasting, recording, things that are easy to forget, our media team taking care of. Is there a clanking sound in the background that any of you can hear?
Yes, yes. I don't know who is the guilty party. I hope it's not me.
I thought maybe it's from my side. I'm seeing there's no sound like that. I'll see who is. Aditya? No, he's also, sorry, he's also muted. Let me see.
So there is some sound at my end, but did it go away when I muted?
This, I can't hear anything now. It's okay now.
Okay, let's see. So shall we get started, Kavita? Are we ready? And
Sure, sure.
yeah, okay. Sushmita, is it okay? Okay. I think you said absolutely, but
Yes,
yeah.
I'm trying to mute myself the moment I stop saying. I'm forgetting. Yes, please start.
Okay. Good afternoon, everybody. I'm very happy to welcome you to the second talk of today's afternoon session. Today we have this session. We have our speaker Kavita Tedikepalli. She is a professor at the School of Technology and Computer Science at TIFR Mumbai, and her research interest is in the broad area of graph algorithms and combinatorial optimization. In this two-part talk, the first part of which is today, she'll be talking about popular matchings and witnesses. And popular matchings have gained a lot of attention in the past decade or more, and we'll be learning about that from Kavita in today's and tomorrow's talk. So without further ado, over to you, Kavita.
Thank you. Thank you so much, Meghna. And thanks so much to the organizers for this invitation and for organizing this workshop. It's been so good. Yeah, so my two talks are on popular matchings and their witnesses. So let's start. So I'll be covering some old work and some new work. So in the first half, I'll be doing some old work, but that will hopefully be a warm-up for the newer part that will come later. So in the first half of the talk, we'll be looking at a bipartite graph where every vertex has a strict ranking of its neighbors, as in this graph here. So this is a very well-studied model in two-sided matching markets, and it has been used in several real-world applications, prominent among them being matching students to schools and colleges, doctors to hospitals, and so on. So one wants a good matching here, and the notion of goodness here is captured by stability. A matching is stable if there is no edge that blocks it. An edge AB blocks a matching M if both A and B prefer each other to the respective assignments in M. The matching on the left, the red matching is stable. It's easy to check that no edge blocks it. While the matching on right, the blue matching, is unstable because the edge between the two middle vertices blocks it. So this is a very natural notion of optimality, and it has so many properties which has led to a lot of study of stable matchings and efficient algorithms for so many problems here. So let's start with the simplest questions. Does a stable matching always exist? Is it easy to find one? In their famous paper from 60 years ago, Gale and Shapley answered these questions, where they said, yes, their algorithm, which is a truly simple algorithm, finds a stable matching always. So this algorithm is essentially vertices in A propose and those in B dispose. Let's run it on the simple example. So the vertices in A, that is little a and S, propose. And the vertex B receives two proposals and B prefers S to A. So B rejects A's proposal and accepts S proposal. And A has no one else to propose to. P never even received a proposal. So we end with this, just the blue matching, which is a single edge. So in all applications, we want large matchings. There may be exponentially many stable matchings, but all of them have the same size. In fact, they match the same subset of vertices. And as we saw in this example, the size of a stable matching could be as low as half the size of a maximum matching. So forbidding blocking edges is a very strong restriction, and it hurts the size of the resulting matching. So some drawbacks of stability are size may not be so good, and perhaps the restriction that it should have no blocking edge is like too strong a restriction. So do we want to empower every edge with this veto power? So can we come up with a meaningful relaxation of stability that includes all stable matchings and shifts the focus from veto power to collective decision? So we want a decision that's made by the entire set of vertices as a whole rather than single edges blocking matchings. And more importantly, we also want to allow for the possibility of larger matchings. And that motivates popular matchings. So we said every vertex has a ranking of its neighbors. That translates naturally into a ranking over all the matchings in the given graph. How does a vertex U compare to matchings M and N? So it just compares its assignments in both matchings, and it prefers the matching where it gets a better assignment. It is a better partner. And it is indifferent between two matchings if it gets the same partner in both. So let's compare any pair of matchings by holding a head-to-head election between them and ask every vertex, which of these two matchings do you prefer? Cast your vote for that. And in case you're indifferent between these two matchings, well, abstain from voting. And let's count the number of votes won by each of these two matchings. So let's check it on some examples. So let's compare the red and blue matchings. When we hold this head-to-head election between them, the top two vertices abstain from voting because they're indifferent between these two matchings. The two middle vertices vote for the red matching, and the two bottom vertices vote for the blue matching. So it's a tie. So we say matching M is at least as good as matching N if the number of votes it wins is at least the number of votes the rival matching wins. So red is at least as good as blue and vice versa. So let's compare the red and green matchings. Well, here the red matching wins the election. So the red matching is better than the green matching because it gets 4 votes. A matching that loses an election is not an interesting matching for us. So a popular matching is one that does not lose any election. A matching M is popular if M is at least as good as any matching. So let's use this function delta n comma M to measure the number of votes of N minus the number of votes for M. So it's a difference between the number of votes that N gets and M gets. And a matching is popular is exactly the same as saying delta n comma M is at most 0. So Garden-Force introduced the notion of popularity in matchings, where he observed that every stable matching is popular. It's a 2-line proof. When we compare any stable matching with any rival, so if a vertex U prefers the rival matching to our stable matching, then its partner in the rival matching, N of U, has to prefer the stable matching to N. Otherwise, the edge between U and N of U would block the stable matching. But a stable matching has no blocking edges. So for every vote that N wins, there's a corresponding vote that S wins. So the number of votes for S is at least the number of votes for N. So I hope this is okay. So every stable matching is popular. Hence, popular matchings always exist because stable matchings always exist. So we are totally talking about bipartite graphs and strict preferences. So these were the properties we wanted, and popular matchings have already ticked the first 2 boxes. So they include all stable matchings, and by definition, they shift the focus from veto power to collective decision. And in fact, stable matchings are minimum size popular matchings. So we have indeed allowed for the possibility of larger matchings. We know there is an efficient algorithm to find a minimum size popular matching. That's the Gale-Shapley algorithm. Is there an efficient algorithm to find a max size popular matching? And in fact, if we want to say this is an alternative to stability, we would like an algorithm as simple as a Gale-Shapley algorithm. So let's be brave and ask the question, can we in fact adapt the Gale-Shapley algorithm to find a maximum size popular matching? So the definitions of stability and popularity seem quite different. Stability seems like a local property. Given a matching, it's very easy to test if it's stable or not. However, popularity seems to be a much more global property. We need to compare our matching against every matching. And in fact, given a matching, how do we test if it's popular or not? And we want a maximum size popular matching. So how do we show no larger matching is popular? So let's begin with this simple example where we ran the Gale-Shapley algorithm. So the maximum size matching here, the red matching, is a max size popular matching. We know running Gale-Shapley algorithm in this instance gives us the single edge SB, the middle edge. How do we adapt the Gale-Shapley algorithm to find the red matching instead? So can we come up with a new graph where that red matching is a stable matching? So in fact, let's think of this extremely simple transformation of G into a bidirected graph. Let's replace every edge UV with a pair of edges, one directed from U to V and the other directed from V to U. So for our small graph, the corresponding graph G prime is as shown here. So there are directions on every edge. And let's say every vertex prefers any outgoing edge to any incoming edge. So the preference order for any vertex is all its outgoing edges in the original order of preference, followed by all incoming edges in the original order of preference. So 1 is the top choice, 2 is the second choice, and so on. So if you look at the vertex B, its top choice was S. So its outgoing edge to S is its number 1 edge. Its outgoing edge to A is its number 2 edge. Its incoming edge from S is a number 3 edge, and incoming edge from A is its number 4 edge. So I've just listed the preference orders of A and B here. So the middle edge was a stable matching in the given graph. However, neither this red edge, the edge directed from S to B, nor the reverse edge directed from B to S, neither of them is stable in this bidirected graph. If we run the Gale-Shapley algorithm in this bidirected graph with preferences as given above, the matching we get is this green matching. And this maps to the matching we wanted to find. So let's just verify. Let's run Gale-Shapley algorithm in this bidirected graph. So both A and B propose along their top choice, that's an outgoing edge to B. And B receives edges along its rank 3 edge and rank 4 edge. And B prefers S proposal to A's proposal. That's a rank 3 edge. So it rejects A's proposal. Now A goes to its other edge, the edge incoming from B. And now B is getting a proposal along a rank 2 edge, and so it prefers A's proposal to S proposal. So it rejects S proposal, and S is forced to propose to its second most preferred edge, that is the edge leading to T, and yeah, that's the end of the algorithm. So we get indeed this green matching. So this was such a simple example. I hope this was clear.
So can I ask one question? So
Sure, please.
In this modified example, we can have a vertex appearing multiple times in the preference list of that vertex. Is that right?
Exactly, twice. That's why I put this superscripts just to differentiate. It's on edges. The ranks are there, not really on neighbors. So it looks upon each of, yeah. So A looks upon B in 2 avatars, one with a minus superscript, one with a plus superscript.
Yes.
Everyone is looked at in like 2 ways. One is you are the recipient, you're the other endpoint of my outgoing edge, and one is you're the other endpoint of my incoming edge. So it always likes B as a superscript minus vertex, like as the endpoint of an outgoing edge. So indeed.
Yeah.
And the preferences are on edges rather than on vertices. So otherwise, if you think of it as on vertices, it's a bit confusing. Now, B seems to be appearing in 2 places and so on. So let's think of it as on edges.
Sure.
Yeah, so this was such a simple example and it works here. Does it work in general? Yeah, so it does. So this is the max size popular matching algorithm in a bipartite graph with strict preferences. Let's construct the bidirected graph where I've just scribbled what I said. Outgoing edges are preferred to incoming edges, and among outgoing edges, it's the original preference order, similarly among incoming edges. Just run the Gale-Shapley algorithm in this bidirected graph. This gives us a matching M prime. In the bidirected graph, just delete those superscripts. So we get a matching in our starting graph. And the claim is, this is a max size popular matching. That is, it is popular and any larger matching is unpopular. So we prove this via the notion of witnesses. So every popular matching has a succinct or compact witness of its popularity. So these were those superscripts that we, unceremoniously deleted as just some waste on top. Actually, that has a lot of meaning, and our matching has this witness of its popularity right there. And so in fact, our algorithm found both a popular matching and a witness of its popularity. So our algorithm computed this green matching, and a witness for this is, so whichever vertex has a plus superscript, take its value. So I'm calling this witness alpha, take its alpha value to be +1, and the vertices that had a superscript of minus, take their alpha values to be -1. So a witness for the green matching is given by alpha A and alpha T are -1, and alpha B and alpha S are +1. So what properties should this witness satisfy? The sum of all the alpha values should be 0, and every edge should be covered by the sum of alpha values of its endpoints. What does this sentence even mean? So given a matching M, let's define a corresponding edge weight function as shown here. Weight of an edge is just the sum of the votes of the endpoints of the edge for each other versus the respective assignments in M. And votes are just 0, +1, -1. +1 means V prefers U to U prime, and so on. So the weight of any edge is +2, -2, or 0. Is this definition okay? And it would be convenient to always deal with perfect matchings. So let's augment G with self loops. And any matching just becomes a perfect matching by just adding self loops at all unmatched vertices. And for any self loop also we need to define its weight. And the weight of a self loop is either 0 or -1. It is 0 if M also left it unmatched, and it's -1 if M matched it to a neighbor. So the definition of this edge weight function was exactly to satisfy this property. For any matching N, if you look at the corresponding perfect matching N tilde, its weight is just this function delta N comma M. It is the difference between the number of votes that N wins and the number of votes that M wins. So M is popular if and only if every perfect matching has weight at most 0 under this edge weight function. So let's write the linear program for max weight perfect matching. It is the simple LP given here. So it's a perfect matching, basically also including self loops. So that's what the first constraint is saying for each vertex. And we want to find a max weight perfect matching under this edge weight function, weight subscript M. And M is popular if and only if the optimal value of this LP is 0. Let's write the dual LP. And these are the alpha values. So they are the dual LP variables. So we want to come up with an alpha value for each vertex such that every edge is covered by the sum of alpha values of its endpoints. That's what the first constraint is saying. Alpha A plus alpha B is at least weight of the edge AB. And we also get the constraints for self loops. Alpha U should be at least weight of the self loop at U. So subject to these constraints, we want to minimize the sum of all the alpha values. So M is popular if and only if there is a dual feasible solution alpha whose sum of where the sum of all the alpha values is exactly 0. So this is a witness of popularity. And the matching M computed by our algorithm has the following witness. For each vertex U, if U plus is matched in our matching M, then its alpha value is +1. If U minus is matched in M prime, then the alpha value is -1. And if U is unmatched, its alpha value is 0. So every edge in our matching in the bidirected graph has the form A plus B minus or A minus B plus. So the sum of alpha values of every edge in our matching M is 0. So sum of all the alpha values is 0 because the unmatched vertices had alpha value 0. So we need to show it's dual feasible, and that follows quite easily from the stability of the matching M prime in the instance G prime. And we also need to show that alpha U is at least weight of the self group. All these are easy to show. So the conclusion is the vector alpha as given by the superscripts is dual feasible, and in fact is dual optimal. Hence M is a popular matching in the given graph G.
Hey, Kavita, can I ask a quick question?
Sure.
Yeah, so does it also speak to like popularity against fractional matchings, like given that you're actually looking at, so it's not popular only among other integral matchings, but
true, but by Birkhoff von Neumann theorem, every fractional matching is a convex combination of integral matchings. So if it's popular over integral matchings, it naturally is.
Yes.
It's popular fractional matchings as well. Indeed. Thanks.
So the witness is the dual optimality.
Exactly. And there is a very simple witness with just 0, +1, -1 values. And but our algorithm was finding that too as the superscript. So it just came to us for free, really. We didn't have to do anything. So Gale-Shapley algorithm gave us both the matching and its witness.
And does the Gale-Shapley itself have a primal dual interpretation?
Oh yes, in the sense. So if you look at this paper by Theo and Sethuraman, they prove the integrality of the. So you're right. It's not the Gale-Shapley algorithm, but there is some. So basically, show the integrality of the stable matching Polito formulation by Rothblum. So there is some kind of a self-dual property that it has. There are some very nice properties, but I agree it's not Gale-Shapley as such, but But to prove that it has that is polytope, that a certain formulation is its polytope, it's an integral polytope and stable matches with extreme points. There are very simple proofs which use this LP and dual. So let me say that.
So you can maximize like linear functions over the space of stable matchings.
Absolutely.
Okay.
So in 92 itself, so we knew how to formulate the stable matching polytope. Indeed.
Okay, great. Yeah, maybe 2 decades later.
3 decades later.
3 decades, yeah. Thanks.
So please interrupt and ask me if there are any questions. So far, I've shown that. So Gale-Shapley algorithm is itself, it's really the one ring to rule them all. So Gale-Shapley algorithm finds a min-size popular matching, that's a stable matching. In the bidirected graph, it finds a max-size popular matching, and the max-size popular matching indeed. And the superscripts of vertices give us the witness that prove that our matching is popular. And I'm yet to show no larger matching is popular. I'm at that spot now. So for any edge incident to an unmatched vertex, the alpha value of all unmatched vertices, that was 0. And while all its neighbors actually are matched, because our matching being stable in the bidirected graph has to be maximal as well. So if U is an unmatched vertex, every neighbor V of U is matched, and its alpha value has to be +1. So the edge UV is slack. The left-hand side sum of the alpha values is +1, and the weight of this edge is exactly 0. So our matching M itself is a primal optimal solution. Alpha is a dual optimal solution, and this edge is slack, which means any matching that contains this edge is less popular than M. It cannot be a primal optimal solution. That's a consequence of complementary slackness, which means any larger matching has to be defeated by M itself. Is this argument okay?
Yes.
Thanks. So it's all so quiet. Siddharth, you gave such a good talk. Everyone participated. I'm giving a monologue. Almost no one is participating. So, yeah.
I was talking about cake, so I guess that just enticed people.
Yeah, so any matching larger than M is unpopular because it has to contain a slack edge. Because its size is larger than that of M, it has to contain some edge incident to an unmatched vertex, and all such edges are slack. And so the matching M itself would defeat any larger matching, which means M is a max size popular matching. And finally, we have a better lower bound on the size of M than a stable matching had. It's easy to show that there is no length 3 augmenting path with respect to M. So if there is a length 3 augmenting path with respect to M, then it would contradict the stability of M prime in G prime. So we would basically have a blocking edge to this matching M prime. It's just the argument is what I've written here. If this is an augmenting path with respect to M, A, B, S, T, then either the outgoing edge from B or the outgoing edge from S would block the matching M prime. But M prime being a stable matching in G prime has no blocking edge, hence there is no such augmenting path, which means the size of M is at least 2/3 the size of any maximum matching is due to lack of length 3 augmenting paths. So we were unhappy that a stable matching had a guarantee of only half. A max size popular matching has a guarantee of 2/3. Am I halfway into the talk, Meghna?
Almost, yeah.
Okay, thanks.
You have 4 more minutes to go to halfway.
Okay.
Yeah.
So now I want to change the model a little. We'll move from the model of two-sided preferences to one-sided preferences. So here we are again given a bipartite graph, but it's only vertices on the left who we call agents that have preferences. Vertices in B are objects, they're inanimate, they have no preferences. Such a graph is also called a house allocation instance because it arises in campus housing allocation in universities. So we want, again, a good matching here. So people have preferences over apartments. How do we allot apartments to various people and keep them all happy? The notion of popularity is relevant here as well. And in fact, popular matching algorithms were first studied in this model of one-sided preferences. So in this example, the blue matching is a popular matching. However, popular matchings need not always exist here. So this is a big difference from the strict two-sided preferences model. Here, by the way, we're allowed to have ties. Agents can have ties, like the agent A1 has 2 second choice neighbors. So we're allowing for ties. However, it's only one side that casts votes because only one side has preferences. So B basically has no preferences. And popular matchings need not always exist here. So let's look at this simple example with 3 agents and 3 objects. And every agent has the same preference order. B0 is the top choice, B1 is the second choice, and B2 is the third choice. The green matching is more popular than the blue one because 2 vertices, A1 and A2, prefer the green matching. So green matching gets 2 votes and the blue matching gets only 1 vote in their head-to-head election. The red matching is more popular than the green matching. And finally, the blue matching is more popular than the red matching. So we can have cycles and there's no popular matching here. The popular matching problem is, given such an instance, is there a popular matching? And if so, find one. So is there a nice characterization of popular matchings? So it's not difficult to show that. So let's call this edge set E1, the set of top edges. So these are the most preferred edges incident to agents. So if a matching M is popular, then M restricted to top edges has to be a maximum matching in this subgraph. So let's look at the subgraph. Let's call it G1, restricted to top edges. Any popular matching restricted to this subgraph has to be a maximum cardinality matching. But there could be other edges as well in a popular matching. Do we know what they are? So to begin with, let's add a dummy object as the last resort option, one such dummy object for every agent. So we can assume that all popular matchings are A perfect. And from now on, it's only A perfect matchings that are interesting to us. So for any agent, let's define these two sets, f of A, which is the set of A's top choice neighbors, and S of A, which is among non-critical vertices in this subgraph G1. Let's look at A's favorite neighbors. A vertex is non-critical if it's left unmatched in one or more maximum matchings. So a critical vertex is one that's matched in every maximum matching, and a non-critical vertex is not necessarily matched. So it's left unmatched in at least one maximum matching. So let's look at A's favorite neighbors among non-critical vertices in the subgraph G1. So a simple characterization of popular matchings was shown, in fact, it's not so many years ago now. So this is joint work with David Abraham, Rob Irving, and Kurt Wilhelm. So M is a popular matching in an instance with one-sided preferences if and only if M restricted to top edges is a maximum matching in this subgraph, and every agent has to be matched and its partner has to be either a vertex in F of A or a vertex in S of A. So every agent is matched either to one of its top neighbors or to one of its favorite neighbors. That's a non-critical vertex in the subgraph G1. So this immediately results in an efficient algorithm. So let's compute the set of edges E prime. E prime is a set of all those edges AB, where B belongs to F of A union S of A. So come up with this subgraph G prime. Find a maximum matching here. And if it's A perfect, return M. That's popular. That follows from the characterization. And if the subgraph has no A perfect matching, again, the characterization of popular matching tells us there's no popular matching here. So it's easy to identify non-critical objects. So that's what I try to write here. So let's take any maximum matching in that subgraph G1, and let's look at all vertices reachable by even length alternating paths with respect to M1 from an unmatched vertex. So that's exactly the set of non-critical vertices here. So in fact, the running time of this algorithm is exactly that order, that just constant times the complexity of finding a maximum cardinality matching. So it's an order m square root 10 running time algorithm. Is this okay? So I went into the past 2007 or so, because finally I'll come to some very recent work that is in a way closely related to this problem. So it's again one-sided preferences. We have a bipartite graph with one-sided preferences. Ties are allowed. But here we say cardinality is more important than popularity. So we somehow said stability was not so good with respect to cardinality, and that's how we motivated popularity. And now we're saying, well, even popularity is not giving us maximum cardinality matchings. Suppose cardinality is the most important attribute of a matching. That's more important than stability, popularity, everything. It's only maximum matchings that are interesting to us. Only those are feasible solutions. So what we want is a maximum matching such that there's no maximum matching that's more popular than our matching M. So M need not be popular. A smaller matching can defeat M. So there are many applications where the size of the matching found is the most important attribute. So they include house allocation problems. Of course, you want everyone to get houses, assigning staff to hospitals in emergencies, and many others. So we always want a maximum matching in these applications. And among maximum matchings, we want a best one. So we seek popularity restricted to the set of maximum matchings. So a matching M such that no maximum matching defeats it. M is at least as good as all maximum matchings. So again, by adding some dummy agents and objects, we can assume without loss of generality that G has a perfect matching. So what we seek is a popular assignment. So the popular assignment problem is the following. Given a bipartite graph with one-sided preferences, is there a popular perfect matching, a popular assignment? If so, find one. So unlike the popular matching problem, we don't have a combinatorial characterization of popular matchings. So there we had a very clean characterization. We said every agent has to be matched to a neighbor in f of a union s of a. Here we have really no idea how does one characterize a popular assignment. So in fact, the first half of the talk where we talked about the max size popular matching, it was basically to familiarize you with witnesses. We'll use the LP method to solve this problem. And yeah, interestingly, the popular assignment problem is a generalization of the popular matching problem. Again, by assigning dummy agents and dummy objects appropriately, you can actually capture the popular matching problem as a special case of the popular assignment problem. So this is a more general problem. So let's see. Let's define an edge weight function in G as we did before in the first problem, where the weight of an edge is just A's vote for B versus his assignment in M. So it's +1 if A prefers B to its partner in M. It's -1 if A prefers its partner in M to B, 0 otherwise. So for any assignment, an assignment is nothing but a perfect matching. For any perfect matching N, its weight under this edge weight function, weight M, is just the difference between the number of votes that N gets and M gets, that is delta N comma M. So M is a popular assignment if and only if every perfect matching under this edge weight function has weight at most 0. So let's write the LP. I'm just mimicking what we did in that problem. So, but in that problem, we already had an algorithm and we're looking to prove its correctness. Here we don't have an algorithm and we're trying to get ideas from witnesses in order to design an algorithm. So things were the other way around here. So let's write the LP for max weight assignment. That's what is given here. It's exactly what we saw before. It's only that the edge weight function is different here compared to there. It was +2, -2, 0, and also along self loops. Here it's what was defined in the previous slide. So M is popular if and only if the optimal value of this LP is 0. Let's try the dual LP. The dual LP here is even simpler than earlier. Earlier we had some extra constraints saying alpha u has to be at least weight of the self loop. Here we don't even have those constraints. So the dual LP variables are the alpha values. Come up with alpha values, one alpha value for each vertex, so that every edge is covered, and minimize the sum of all the alpha values. So M is popular if and only if there is a dual feasible solution alpha whose sum of alpha values is 0. So we can in fact show that there is a nice looking dual feasible solution. So if M is popular, then in fact there is a dual feasible alpha such that the alpha values of all agents, so I'll call vertices in A agents, alpha values of agents are in the set 0, 1 till n-1, and alpha values of objects, so vertices in B are objects, so they are exactly the minuses of those values, 0, -1 till -n-1. So the proof is not hard. It again follows from complementary slackness. For any edge in our matching M, we have tightness. And so in any constraint for an edge involving incident to B, I can replace alpha B with -alpha A. And because the edge weights are in the set 0, +1, -1, it's easy to argue that for any two distinct consecutive values, alpha A and alpha A prime, it's enough to keep the difference to be 1. That's enough to cover all the edges. So there is a nice looking dual feasible solution. So the graph may not even have a popular assignment, but if it has a popular assignment, the popular assignment has a nice structured witness where the alpha values look as given here. So how do we use this to design an algorithm? So we don't have the algorithm. So let's interpret these alpha values as levels in a graph. So level 0, level 1, level 2, so on. So I want to come up with a subgraph of G and somewhat reduce the popular assignment problem to a perfect matching problem in that subgraph. So suppose somebody gives us a level function on the set of objects. So for every agent, let's define L star of A to be the highest level at which it has a neighbor. So L star of A is maximum of the levels at which any of A's neighbors sits in. So L is a function that's given to us on the set of objects. So let's consider the following subgraph G sub L. So what are the edges in this subgraph G sub L? For any agent, keep all its edges to its most favorite neighbors in the highest level. And let's look at one level below in the level L star A minus 1. Let's keep A's edges to all its favorite neighbors in that level, provided these neighbors are preferred to all the top level neighbors. So for every most preferred neighbor B prime of A in level L star A minus 1, if A prefers B prime to all neighbors in the highest level, then keep this edge in this edge set. So let's do it on an example. So there are two agents here, A1, A2, and these numbers in the squares denote the levels of those respective objects. So there are two objects in level 0, one in level 1, one in level 2. And the numbers on edges denote preferences. So these 1, 1, 2, 1, 3, 2, they're all preferences of the corresponding agent. So L star A1 is 2 and L star A2 is 1. They are the highest levels at which these agents have neighbors. So note that A1's neighbor in level 1 is less preferred to its neighbor in the highest level, because its neighbor in level 1 is a rank 3 neighbor, and its level and its neighbor in the top level is a better neighbor, rank 2 neighbor. And moreover, its top choice neighbor is in level 0, which is 2 levels below the highest level. So neither of these dashed edges is allowed to be in our subgraph G sub L. And all the bold edges are in E sub L. Is this okay? So I'm defining this graph G sub L as shown in this example. So every agent keeps edges to its favorite neighbors in the highest level, and in highest level minus 1, if that neighbor is preferred to all the highest level neighbors, it keeps an edge. Otherwise, it doesn't.
And at the moment, we are assuming that the levels of B's are given to us.
Exactly. Indeed, indeed. We're assuming that if you are given such a level function, how do we build the corresponding subgraph G sub L? Exactly. So the claim is perfect match. Sorry.
Just one question. In this diagram, from A2's perspective, its most preferred partners are in level 0, right? So
That's
why
correct.
is that 2 marked edge, a dotted edge also? Why is it still in EL?
So it doesn't have any neighbors in level 2. So it only looks at its own neighbors. There may be other neighbors in level 2, but they're not its neighbors. I mean, it has no neighbors in level 2. Its highest level for a neighbor is level 1, and this is only one level below highest level.
Oh, right, that point. So if it's just one level, then you keep it. If it's 2 levels up, then okay. Sorry.
Exactly, exactly. So we are allowed to keep edges only to the highest 2 levels. Anything below, anything below that is not possible. Highest level, you always keep edges to your favorite neighbors. Highest minus 1, you keep edges provided they are better than your favorite neighbors in the highest level.
Right.
So if M is a popular assignment, then in fact M is a perfect matching in this subgraph G sub L. And this level function then would be given by the witness actually. And conversely, if someone comes up with a level function and gives us a perfect matching in the subgraph G sub L, then in fact M is a popular assignment in the given graph. So basically our algorithm is, can we find a level function so that G sub L has a perfect matching? Then that's a popular assignment. So let's try to find a level function. Let's initialize the level of all objects to be 0 to begin with. And let's compute a maximum matching in the subgraph G sub L. If it's perfect, wonderful, return it. Else, increase the levels of all unmatched objects by 1. So that changes the subgraph G sub L, it gets updated. Go back to step 2. Compute again a maximum matching in the new updated subgraph G sub L. If it's perfect, job done. Else, increase the levels of all unmatched objects by 1. Go back to step 2. So eventually, either a perfect matching M in G sub L is returned, or the level of some object becomes N. In the former case, M is a popular matching, and we also get a witness along with it, and the witness is exactly given by levels. So alpha B will be minus of the level of B, and alpha A would be level of its partner. It's a perfect matching, so everybody has a partner. So alpha values for agents are just levels of their partners, and alpha values of objects are minus of their levels. And in the latter case, we show G has in fact no popular assignment. So it's not that we failed to find one, but actually G has no popular assignment. So this is our popular assignment algorithm. This is joint work with Thomas Kirai, Yannick Matushke, Ildi Schlöter, and Ulrike Schmidt-Kreplin. So this is the pseudocode of the algorithm. It's essentially what I wrote in the previous slide. So start with levels of all objects are 0. And while there is an object, while all objects are at level strictly less than n, construct the subgraph G sub L, compute a maximum matching. If it's perfect, job done. Else, for all unmatched objects, increase their level by 1. And so either we return a perfect matching, or the level of some object becomes equal to n, in which case we return G has no popular assignment. So this can be solved in polynomial time, but it has a rather high running time. So we run the maximum cardinality matching algorithm n squared times. So its running time is m times n to the 5/2. I'll discuss all this in tomorrow's talk, prove the correctness of this algorithm. Right now, I'm just saying it as a black box. And an interesting open question is there a faster algorithm for this problem? So what happens when G has no popular assignment? So why don't we ask for an approximately popular matching? So how does one measure that? So a natural measure of the unpopularity of a matching is its margin. Mu of M is the unpopularity margin of M, which is defined as follows. It's the largest margin by which another assignment defeats M. And an assignment is popular if and only if its unpopularity margin is 0. So the K unpopularity margin problem is, given a bipartite graph with one-sided preferences, does it admit an assignment with unpopularity margin at most K? If so, find it. So we use the same method again, we come up with the same edge weights. And in fact, a matching, an assignment has unpopularity margin at most K, if and only if the optimal value of this LP is at most K. So it's exactly what we did for popular assignments, but instead of optimal value being 0, here I can only say, because the largest margin by which another assignment defeats it, and the optimal value of this LP is exactly that. It is max over all assignments n, delta n comma m. And the optimal value of this LP is at most K, it means M's unpopularity margin is at most K. Let's look at the dual, the same method. And so here we don't have as much structure as before. Earlier, the alpha values of agents were 0, 1 till n minus 1. Here I have some slack, it's n, but the alpha values of objects are 0, minus 1, minus 2 till minus n minus 1. So M has unpopularity margin at most K, if and only if there exists a dual feasible alpha such that sum of all the alpha values is at most K, and in fact alphas have this structure. And so this algorithm is a little more detailed. It is not as simple as the previous one. So I'll just state it as a black box. I'll not really show the pseudocode of this algorithm. Our earlier algorithm can be extended to show an algorithm with running time m raised to k plus 1 times n to the 5/2 for the k unpopularity margin problem in G. So this is, of course, the dependence on k is exponential, which leads to the next question. can we show an FPT algorithm for the K unpopularity margin problem? So to begin with, the K unpopularity margin problem is NP complete, even for strict preferences. And in fact, it's W1 hard. So it's very unlikely it has an FPT algorithm. In fact, we have a stronger lower bound. In fact, it's highly unlikely that it has an f of k times m to the little o of k running time algorithm. However, this assumes that the preferences are not strict. An open question is the K unpopularity margin problem in FPT with parameter K when preferences are strict? So we don't know the parameterized complexity of this problem for strict preferences. When preferences have ties, it's not likely to have one. So that's the end of my talk. So these are the references. The popular matching algorithm from 2007 is with these collaborators, and the popular assignment problem is with these collaborators. Thank you.
Thanks a lot, Kavita, for the great talk.
Oh, thank you.
So maybe I'll ask if there are questions in the audience.
Hello, I'm audible.
Yes, yes.
Yeah, so I had one small doubt in that we were finding max size popular matchings.
Sure.
We were building a graph with bidirectional edges and finding a stable matching in that. So
Sure.
does it work so we were saying that any stable matching in G prime is a maximum popular matching in G.
Absolutely.
Does it work backward, like every maximum matching in G is stable matching?
No, not really. It's a very good question, and it's not so. So it's not the case that, so basically,
if I know, it's for dominant matchings that work that way, right?
Exactly.
Okay.
So it's basically those max size popular matchings that defeat all larger matchings that can be captured in this manner. That's exactly the class of dominant matchings. So there can be max size popular matchings. They do not necessarily defeat all larger matchings. So they are not captured as stable matchings in this bidirected graph.
Yeah. Thanks.
So I had a related question. So
Sure.
in this same model, we can compute amongst all the maximum cardinality matchings a popular matching, right?
That's right.
Does that algorithm also have a similar dual, witness or something like that?
Yes, indeed it does.
Okay.
Exactly.
And it can.
Meghna's question is in two-sided preferences, right?
Yes, two-sided preferences. Yes.
Exactly.
Yeah.
Exactly. So in fact, that work preceded this work. So that in fact gave me ideas. So the popular assignment problem, the machinery we use, everything actually was very much motivated by analogous work for similar things for popular matchings within the set of maximum matchings in the two-sided case. Exactly.
Yeah.
So another open problem is there a combinatorial characterization of popular assignments? So of course the LP method is very clean, but it's a very opaque method, right? We do not know really how a popular assignment looks like. Whereas a popular matching, we very nicely know that every agent has to be matched to a neighbor in F of A union S of A. Out here, so in fact the LP method, it's so powerful, so useful, but it's very opaque. So that's my feeling, that it would be nice to have a combinatorial characterization. So our algorithm is of course totally combinatorial. We're not solving any LPs in our algorithm. The algorithm is as simple as the pseudocode here.
And it also has this similarity of keeping the edges of the topmost level and the second level. So
here they're not really speaking the top choices. It's only the levels that indeed there is a similarity with popular matchings, but popular matchings are saying keep edges to your top choice objects. So in the highest level, it need not be your top choice object. You may not even have an edge to your top choice object, as in this example here. So here A1 doesn't even have an edge to its top choice object because it is in level 0. It's the levels here rather than its own ranks or preferences. But yes, it would be nice to have a combinatorial characterization of popular assignments. So though we can solve this problem, we don't really understand the structure of popular assignments. And that may lead to a faster algorithm for the problem.
So, quick question, maybe like a digression, but in general graphs, stable matchings don't exist, but even popular matchings might not exist.
Exactly, and that's an NP-hard problem. So stable matchings, there is an efficient algorithm to decide if one exists or not.
Right.
There's, in fact, several efficient algorithms to decide. But for general graphs, the existence problem is NP-hard. So Sushmita and her collaborators showed this. We also showed it. Many of us showed it around the same time.
Okay. And so the other question is that, so here you're using like a standard counting voting rule to determine, like, but there are, like, not an expert, but there are a lot of other voting methods. In particular, you could account for how good a preference is, like use that as, say, a Borda count. Like you could use other voting mechanisms to like quote unquote rank matchings. So has that been considered? Or?
Oh yes, so Rohit, Vash, and I actually considered the Copeland's method, but they turn out to be even more intractable, you know.
Oh, okay.
So in fact, because the set of matchings is exponentially large, right? So there are exponentially many candidates, and now to decide who is a winner, it's all very tough, very hard problems.
Okay, and does this like so the stability as a construct doesn't like naturally extend to other settings, but has there been work on looking at, for example, popular spanning trees and so on? So
yes, indeed. So there has been some work, but there were some hardness results, I think, on some popular spanning trees. But quite recently in 2020, with the same set of collaborators actually, Tamas Yannick Madushke, Ildi Schlotter, and Ulrike, we looked at some problem called the popular branchings problem. So branchings are exactly our forests, directed forests. So we in fact gave a polynomial time algorithm to solve the popular branchings problem.
Okay.
So we said, in fact, popular branchings occur in liquid democracy. So we have to finally come up with a story to justify it, right? So, and for that, there was actually a story coming from computational social choice. So in liquid democracy, if you want to transfer your votes, so the directed forest is basically capturing that. So is there a way of transferring your votes so that it's a popular branching? And we had a polynomial time algorithm for that problem. That's also completely motivated by the LP method and witnesses and so on and so forth. So this method is actually quite powerful. So wherever we have a good understanding of the LP for the original problem, in this case, the LP for bipartite matchings. Understand, we take the dual, they form witnesses, and a popular structure in the case of branchings, a popular branching or a popular matching is a self-optimal solution. Its own incidence vector is an optimal solution of the primal LP. So that gives us lots of nice properties by complementary slackness. So I think Amit would have said his theme is going to be linear programming. So I'm already saturating people with linear programming. So it gives us so much power, and things follow quite nicely, but nonetheless it is opaque was my complaint. That's all. We don't really understand how solutions look like.
Yeah, thank you.
Somewhat related question, like is there any work on the structural characterization of the set of popular matchings on the one-sided preferences?
On the set of popular matchings, it all follows from this combinatorial characterization, right? So, in fact, popular matchings, we understand them really well in one-sided preferences. So we know that every popular matching has this structure. So if you want to find a minimum cost popular matching, all you need to do is just optimize over these matchings. It's very easy to describe the set of all such popular matchings. Is it okay? So just write. So they can use only these edges. So any popular matching has to be A perfect. It has to match all the agents and it has to use only these edges. So all these are very nicely captured by a linear program. And so you can describe the set of all popular matchings exactly as a set of feasible solutions of the linear program, and you can optimize over it. So for popular matchings, things are really well understood because of this combinatorial characterization. For popular assignments, we don't have such a characterization. That's what I was trying to do.
Thank you.
Thanks a lot once again, Kavita. And
Thank you.
yeah, and so we'll close the session for now. And I guess we are meeting at 6 p.m. Sushmita, is that right?
We'll log in slightly before 6 p.m. So the next talk, the last talk for the day will be at 6 p.m. It'll be by. I just wanted to add that a lot of majority of our audience members are actually students, and at least in our institute, some of them have been introduced to LP method in the first semester, to ILP and linear programming and so on, right? At least at the very introductory level. So this is reinforcing that they should pay more attention. This is a wonderfully powerful technique. So today's day, I think, just reinforce that point. Okay, so then we meet at slightly before 6 p.m. I look forward to all of you again joining us. Bye and see you then.